Yeah, I'm Michael Lynch. I've been sort of in the Clarion orbit for a few years when it was decided to have Clarion rewritten from the ground up in C#, as it turns out. I'm not going to talk much about implementation issues. That's going to be coming up over the next 2 weeks, so this is mostly the high-level overview. This tutorial is based on a slide set that Ron polished, I guess, around last October, and that was a 6-hour or so-called full-day tutorial. This is going to be a half-day, so I've elided a lot of slides, mostly the mathematical slides. We won't get into that too much, but Ron's tech spec certainly gets into the math in as much detail as you care to look for. Anyway, that's what we'll do today. There are several modules. We'll talk about the major components of Clarion, take frequent question breaks along the way, and we'll see if we can finish up by the time we have allotted. Before I start, any questions about anything generally, before I get underway? Yes?
Why did you choose to use C#?
That's a technical matter, but I can basically give you the overview. It was originally written in Java, which is basically okay and it's available on everything, but there are issues with what Java can support when you're doing AI-style code. There was a technical decision we made a couple of years ago to switch over. We've been very happy with it. I'm sure Nick will get into it a lot more, though, when we get into the implementation stuff. C# is fine to learn if you know Java. There are things about C# though that make it more expressive, we think, than Java. But I'll defer those more detailed issues with that to Nick when he gets up next week. Okay, any other questions? Okay, let's start. About 20 minutes on the introduction, about an hour on the ACS, or Action-Centered Subsystem, another 40 minutes on the NACS, the Non-Action-Centered System, about another 40 minutes for the MS and MCS, and about 10 minutes of conclusions, and that'll be roughly about 4 hours of work. We'll start with, of course, an introduction to the overall thing and the theory behind Clarion, or what's propelled Ron's son in particular to build Clarion. Ron was trying to build a cognitive architecture, which is all those things you see there, broadly scoped, domain generic, computational model in a way that can be used in lots of kinds of research areas, or ultimately in the Clarion library as a way of building AI type of applications. And it's designed to be quite general purpose in that regard. It's not purpose built for any particular domain. That's one issue there. A cognitive architecture, of course, is typically a large body of code that's not unlike the architecture of a building. You have foundation, floors, walls, ceilings, etc., and we keep the same idea here. A point to keep in mind about Clarion is that it is propelled by psychological theory and attempts to explain psychological phenomena. It doesn't really approach the issue here, as you might say in AI, where you just simply want a good algorithm which not necessarily matches what a human would do. So, for example, a pathfinding algorithm in AI would be A* typically, or some variation. Humans don't think using A* algorithm to pathfind, but because it's efficient and effective to use it in AI, you can use it there. That kind of approach isn't used here. We're trying to model human behavior. So that's a key distinction between an AI package, if you will, and a cognitive architecture. And these other points here are also there too. We want this to basically work. We're trying to provide a framework to facilitate modeling and exploration of the various aspects. I have to kind of read this way because this cord's not long enough. My apologies here. And we're trying to actually get this to work that way. We're trying to provide an essential framework that you can do cognitive modeling problems on and incorporate the psychological theories that they're built on top of. So that's really the motivation for building Clarion. Now, why are they important? Well, that's kind of where we are in some respects in cognitive science, is that we need to be building models, and models that can, in detail, explain phenomena that we observe. And what many of the simulation problems that have been run in Clarion in the past and currently are about modeling experimental data that humans yield and trying to match that with a model that we can construct in Clarion. So the two things together are what we're trying to do when we're doing cog-site research. We run an experiment, we have several examples we'll be getting into, and then we try to replicate the behavior as if, in Clarion, as if it were behaving like the human. And in general, we find that these models give us pretty close fit, which is, of course, a success factor for us. Of course, you can do similar experiments with ACT-R and SOAR, but we're using Clarion, of course, here. So this is what we want to do, and Clarion is quite general purpose. We want to move this towards areas considering personality, emotion, social interaction. We're trying to be able to eventually tackle large problem sets or domains with Clarion that maybe lesser systems can't really handle. Yes?
So the way that you evaluate whether or not this cognitive architecture is performing in human-like manner is if it gives results on tests that you could give to a person similar to what you would expect a person to give?
Exactly. Like something like the Wegner study, for example, I guess Shane is currently working with. We get data collected from humans, and we can look at things, for example, like response time or error rates and so forth. And then in the Clarion model you build that replicates or attempts to replicate processes going on, we would expect to see similar response times or error rates, for example. And if we get a good fit, well, that's not saying that we've exactly captured everything about the human cognition going on, but that our model at least is able to cover that kind of performance. This is a tradition that is also found in ACTAR and SOAR research. You find the same sorts of things being done there. And so we're not trying to get, as I say, a robust, error-free AI kind of a thing going on. We're trying to get a replication or a simulation of human cognition. Does that answer the question? Okay. So that's what we're trying to do here. And so we're trying to build these elements into here, and that's, I think, what we got here. Now, of course, the claim that Ron Sun advances is that there's plenty of room to be doing this. Of course, we have a hell of a time trying to analyze what the human brain can do. Our tools for getting inside the operation of the brain, fMRI and so forth, are really still in their infancy. They're quite limited. We don't really understand all the inner workings. And let's face it, we're kind of at the infancy of all this at this stage of the game. But we can build models, and as our computational power increases and our resources for that increase, we can build more sophisticated models. And Clarion attempts to be one such model. It's a true hybrid architecture. It has top-level symbolic reasoning systems, and it has bottom-level neural net, basically connectionist systems, and an integration between the two levels. And that's going to be a lot of what we spend time on today. And that's really one of the things we want to be able to do with this system. So Clarion is an example of that. The four components in there, there are four major subsystems. We call them the ACS, the NACS, the MS, and the MCS. You can see the full spellings there. And these are the components that make up any Clarion agent. You could build a Clarion agent with nothing more than an ACS, basically just an action-centered subsystem, which you're basically building as a reactive agent that is capable of learning, but you can't get into the more sophisticated human cognition issues that you might be interested in investigating. If you want to get into those, for example, reasoning over a large knowledge base, you would have to invoke an NACS, and so forth and so on. And this will be clearer as I go along. I don't think that's going to be a problem. So those are the major components. We'll look at a top-level diagram shortly about that. So each of these subsystems, in fact, incorporates two levels. And we use the term level intentionally here to sort of signify that the top level encodes explicit knowledge. It's symbolic-based kind of thing. This is what, for example, a architecture like SOAR would attempt to do, which is pure, rule-based kinds of reasoning. Whereas the bottom level is built out of neural nets. And we have several varieties of neural nets in Clarion. You are able, in the implementation, to customize these to your heart's content, and that's kind of how it was architected. But all the four subsystems have this dual level architecture about them. And it's based on a rather long set of traditions in cognitive science, which is extensively documented in Ron's work, various motivations and justifications for why this approach is appropriate. And of course, in the Psychological Review article in 2005, Ron's son really explicates this in considerable detail. Another point is that these two systems are not independent of each other. There is bottom-up and top-down flows, if you will, between the two levels, which gives the subsystem its really its capabilities, and that will become more evident as we go as well. So here's the top-level diagram. There's a lot going on here. We'll return to pieces of this as we go. But in the upper left is action-centered system with centered spelled in the British manner. And essentially, we have explicit representations at the top level and neural net representations at the bottom level, the explicit and the implicit levels over here and over here. And as you can see, there is a bidirectional connection between the two. The NACS is somewhat analogous, but it's going to be about a different body of information. The action-centered subsystem really incorporates procedural knowledge, procedural knowledge on how to do things in the world. Whereas the non-action-centered subsystem really is concerned with declarative knowledge and episodic memory. So those other kinds of knowledge systems or memory systems are found there. The third module is motivational, and this is how we manage drives and goals in Clarion. Again, the goal structure is basically at the top level. These are the things that the agent is going to attempt to do or satisfy. And the drives are more neural net based, and those are going to guide how goals are selected. Finally, there's a monitoring subsystem, or we'll call it loosely monitoring, which we call the MCS, the metacognitive system. And what this component does is monitor and maybe perhaps alter the ongoing performance of the system by perhaps changing parameters, applying filtering to various flows inside the system, and so forth. Another point, yes?
So is it purely architectural? Is it purely a computer science role that that's filling, or is it also doing metacognitive functions that a human mind would?
That's a tough question. Basically, it does. Of course, the metacognition system, in terms of its implementation, is a collection of components, which you could include or not include as you saw fit, and you could write your own special components for some particular domain that you thought was interesting. It's somewhat of an umbrella term for all the various kinds of things which may reside in different parts of the actual brain. One point to make about Clarion is that it is not really attempting to map itself onto the actual various structures inside the brain itself. There's no neurological basis per se, it's more psychological. This could be a thing you could argue should be done differently. It would be an open question. But in terms of what metacognition means here, we're going to see quite a bit of that later on. But there's all these different aspects are things that you can activate within a Clarion agent if that sort of behavior is something you need. So there's a bit of a, in order to just make the process practical, you don't have any CPU cycles per second that you can get, you may need to exclude things that are not germane to what you're studying. But it is essentially at this point a collection of metacognitive functions, and they are in or not in as you see fit. Does that really get to what you're asking? Okay. And so this is basically the picture. Here's a more recent picture. It's sort of I'm not sure why we need two slides here, but I'm going with the slide set. This is just a more modern illustration, but more or less captures the same notions. I should point out, I'll go back to the original, from the left-hand end is what comes in through the sensory apparatus, and these are fed into three of those four subsystems, the ACS, the MS, and the MCS. Those can actually receive sense data from the world. Now we're going to see in a little while that the way Clarion works with sense data is kind of interesting because we have the notion of chunks and dimension value pairs. What's basically going on here is that you don't really want to use Clarion for things like low-level visual processing. You, in principle, could, but if you're trying to do, edge detection and a lot of complex visual processing, you would probably want to relegate that to some other way of doing it, and then have it featureize the things that are in the scene that you're trying to perceive, and it's the features that are being fed into Clarion. So Clarion is more top level in the way it operates, and it's not quite trying to be like, here's your handy way of actually doing heavy-duty visual processing. Do that some other way, and then featureize what you're seeing, feed that as input data into Clarion. And as I say, these arrive at three of the subsystems in order to create various effects, if you will. Different sense data can affect how drives are going to operate or how they're going to unfold. They may affect how the MCS wants to alter the behavior of the organism or the agent. And of course, the ACS directly gets sense data because, of course, it needs to perceive the world, decide what to do, and then act on it. That's the primary purpose of that. So we'll go by that slide there. So we basically have in Clarion a distinct dichotomy between, implicit and explicit processing. This permeates the architecture and is, in fact, one of its strongest features. Clarion was doing hybrid architectures before that became fashionable, long before any attempt by Actar or SOAR to get into that area. We want to look at the cognition, motivation, environment interaction. As you'll see in the next couple of weeks, you build a world. The world contains data that is perceivable by an agent, and then the agent is able to act on the world. It's that, of course, kind of perception action that we care about here, if you will. And we're always looking at the interaction of all these modules. Upon receiving sense data, quite a lot can happen inside the agent based on the flows you set up. It might be just a reactive ACS agent, but if not, there's much more going on. For example, a given sense data may cause several rounds of reasoning to take place, in which case you may see an action that comes through several steps or several cycles of thinking about the action before an action is actually issued by the agent. Again, these are things that will make more sense when you start seeing some of the implementations. Also, it does learning. This is an architecture capable of doing learning, so there is both a bottom-up and top-down several techniques inside of the engine that let you provide for learning in various ways. More on that a little bit later on. And these are, again, part of the main things in Clarion. So we'll look a little bit at these systems, and this will conclude the introduction, I guess, just to sort of get you oriented. Then we can do some more questions. Essentially, the bottom level of the ACS is going to be, again, neural net. These are where you can do pure reactive kinds of agents here. And of course, you can do reinforcement learning on that. It's modular. You can build in one or more neural nets. You can have as many neural net subcomponents within your ACS as you need. And nothing limits you in that regard in terms of how these systems are architected. The top level, of course, is more your traditional rule-based kind of a system here. And these are also expressions of taking sense data, finding a matching rule, and then possibly triggering an action. That's not all that goes on. There's more to it than that, but that's basically what the top level would do. And of course, there is that communication across the levels. You have bottom-up learning, top-down learning, and two other kinds of learning here that we have, independent hypothesis testing and other things that you could additionally implement if you wanted to. I'll leave those details for another time, and we're not going to get into that today. There's no time to do that. Basically, the bottom-up learning process is essentially operates roughly this way. If the neural net actually triggers an action and the action is successful in the world through a feedback mechanism, then it's possible for it to potentially extract a rule, which is a rule that could be expressed in a symbolic way. And then, of course, when the rule shows up at the top level, it is potentially eligible for being selected in the future. If that same pattern of sense data arrives, you can get the same action triggered by operating at the top level. Now, it's possible that not every sense data that led to a successful action will invariably lead to a successful action. It's possible for it to lead to an action that fails. So there's more going on with this, and there's a component in there called the rule extraction and refinement, or RER, which gets into how that behaves. Other things are going on too. You can collect statistics and so forth. Are these slides being made available on the website later? Okay, great. I wasn't sure if they were. So bottom-up learning is how you can essentially take some rather fuzzy or ill-defined or wet, if you will, kind of a set of connections between sense data and recommended actions, and then from that actually extract from that a rule you can talk about, and that would be basically learning something. One of the scenarios that Nick will be running in a couple of weeks, or next week, will be XOR, exclusive OR. Now, you all know what exclusive OR is a logical operation, right? If the two things are 0, 0, or 1, 1, if you give two binary inputs, then exclusive OR says false. If you get 0, 1, or 1, 0 as inputs, then exclusive OR says true. That's your basic exclusive OR logical operation. With the example you'll see, exclusive OR is simply going to be done by training a neural net to give you the correct answer when you submit a binary 1 or 0 and a second input of binary 1 or 0. It should give you the correct answer after a lot of rounds of training of the neural net. But along the way, what the agent will do is learn the rule for exclusive OR. It'll actually extract from its learned behavior in the neural net the fact that you have, gee, if I get a true and a true, I should yield false. If I get a true and a false, or a false and a true, I should yield true. And if I see a false and a false, I should yield false. It'll actually learn this and express it in a symbolic fashion. Now, it doesn't do that because you gave it that. It does that because it actually learns this from what the neural net has learned, and finally finds a rule that expresses that in a symbolic way. It's kind of an interesting thing, and it's really quite fun to see it happen because it really works. And then more can happen beyond that. I'm probably getting ahead of myself on that story, though. Other things that go on here, simulations. Okay. Essentially, Clarion can learn even if you don't give it feedback. There are ways of making that happen. You can also put other kinds of learning in there. There are two other mechanisms called IRLs, independently learned rules, and fixed rules, where you can bake, if you will, rules into the system or provide a population of rules that it can then try out in the world, and then from that decide whether it to keep a rule or change the rule possibly. Again, is that all mysterious? Is that too much? I don't know if this is making sense at this level, talking about that. Okay, that's the ACS in a nutshell. The NACS is a bit different. Basically, the NACS works in the service of the ACS. The NACS usually has requests made to it, if you will, via the ACS. Then the NACS is turned on, is devoted to solving the request. Now, the ACS stores procedural knowledge about how to work in the world or operate in the world. ACS deals with semantic knowledge or declarative knowledge and also episodic memory. These are the two main purposes of the NACS there. And various ways of doing retrievals of these data are made available in this subsystem here. At the bottom level, we have associative networks, associative memory, basically hot field networks and so forth that can actually learn patterns of submitted data. So it can begin to discover patterns in an array of nodes that are activated at the bottom level. And then, not unlike what goes on in the ACS, this knowledge can be extracted and floated upward to the top level where it's able to be expressed symbolically, and that's what goes on there. And we do this by, again, that notion that there is a bidirectional flow between the two levels in the NACS. It's also able to do similarity-based reasoning, and now I won't get into that now, we'll do that when I hit the NACS module, but you don't have to always find exact matches to see if a rule should be activated or not, or if a given piece of knowledge extraction or retrieval should happen or not. You can make this a little fuzzier by allowing it to be close, but not necessarily exactly on target. Similarity-based reasoning gets into a lot of interesting complexities that I'm sure Nick will get into later on. We have again bottom-up learning, top-down learning, and other forms of learning potentially available, as well as several ways of doing reasoning inside of the NACS. The motivational subsystem is concerned with why the agent does what it does. Essentially, one of the things Clarion does offer is that the agent can be given purposeful behavior by designing into it collection of drives, and there are a standard set already available, and you can of course customize from there, and then those drives are going to lead to decisions on what goal to pursue, and of course the point of selecting an action is to satisfy a goal which will then presumably reduce some sort of tension between the drive state and where it wants to be. So for example, if the agent finds that it's low on food energy, it'll go seek food. You can make that an action it picks. And we'll get into that a lot more because there's more going on than just that. And of course, the motivational system is also going to be, like all the others, dual representation, top level, top layer, and the bottom level, with explicit and implicit knowledge again. These are basically how these work. More detail on that later on. Within that, we have a distinction between the kinds of drive states we can have. We have those sort of low-level ones, which are things like food, water, oxygen, shelter, things of that nature, and the more upper-level ones, which are more social kinds of drives instead. And we have a theory that Ron has developed a theory which talks to that, and we'll see that eventually it actually leads to models or theories of personality, but that's getting ahead of our story too. And so this idea of a bipartite set of like low-level drives and high-level drives is part of the theory, again, driven by psychological theory that we find in Clarion. And of course, then there are secondary drives, which can be a very, very large number of these, which are derived by particular behavioral things that an agent wants to do. So we can give these, I want food, but I want gourmet food, or I want, food and I'll eat anything. You can make these sort of part of your model depending on how you choose to design your system. Again, I'm getting ahead of myself a bit. Finally, there's the MCS, and this is essentially, you see the quote there, refers to one's knowledge concerning one's own cognitive processes and products and the control and regulation of them. Kind of an older idea, goes back to the mid-70s, but here we have the notion that various elements within the MCS can monitor and alter the ongoing behavior of the agent. One of the long-term design goals of Clarion is to be able to build agents that have the ability to operate for days or weeks on end without necessarily crashing or breaking down. If you think of the kind of problems, for example, a Mars lander or something like that, it turns out to be remarkably difficult to build an agent that is going to run for more than a little while. To build toy systems that run and then they stop running. To build one that actually has an ongoing ability to survive and to operate in the world effectively over days or weeks or months turns out to be a hard problem. And we've hardly made any progress with that with Clarion either. We don't have the resources NASA does. But we do have at least the potential with and that would be kind of why MCS needs to be in here. There is a constant need to monitor what an agent is doing. It needs to observe, if you will, what it's up to and make corrections as it goes in order to respond to changing environmental conditions. Yes?
Stupid question. Does the MCS ever monitor itself?
You mean a metacognition system? I don't think Ron's put that in the box yet, no. But
Well, presumably, I mean, metacognitive subsystem is part of the subsystem as a whole, so it needs to be monitored at least by itself.
Well,
that's a good question.
you
How
run
would
into this homunculus problem when
Yeah.
you try to take this on, all right? The question becomes,
Infinite regress.
where do you cut it off, right? If you have, you know, one thing, you know, which is monitoring something else, then maybe something else to monitor that thing, and something else to monitor that, and so on and so on and so on. It could go on forever.
Arguably,
That being said,
it's just-
there are certainly interactions between the various modules within the metacognitive subsystem. So there is the ability, let's say, for parameter monitoring, parameter updating. There's certainly built into it the necessary requirement for certain modules to require other modules to act first before that module can run. So it needs information which is concluded by a different metacognitive module in order to be able to perform its own process.
Say, for example, the agent does something about a cognitive, the MCS says, okay, no, that's not such a great idea. And so it tweaks the agent, and then things perform even worse. How's the MCS then going to learn? How is it going to be controlled? It's not going to do that again. If the situation goes back to the original parameters revert, how is it going to be
Well,
constrained?
yeah, your assumption there, for one, metacognitive modules, and we'll get into this in a minute, but metacognitive modules act like mini ACSs, which basically means that they're operating the same kind of duality that operates within the ACS, as well as having the same kind of learning processes. So metacognitive modules are able to learn now. They don't learn in exactly the same way as the ACS, right? Because they're learning based off of monitoring of internal internal performance. So if it changes a parameter suddenly, performance isn't done as well. Your assumption here is that you have a metacognitive module which is monitoring performance, and then that metacognitive module would say, oh, that's not so good, and provide a reinforcement signal to the module which changed that parameter to begin with. So it would say, so it would give something like a negative reinforcement and say that was a bad change. That would then make sure that change, a change like that doesn't get made again. And the system which is, making these parameter changes will therefore the next time around change the parameter to something different. To keep in mind that these modules aren't one-offs, right? They're always running every single time step.
I'm aware of that.
So.
Okay, sure. So we'll get into this more later on, but here are basically the catalog, if you will, of metacognitive functions you can have. Behavioral aiming, information filtering, information acquisition, information utilization, outcome selection, cognitive modes, and altering parameters in a variety of ways inside of the other subsystems, the ACS and the NACS. Don't worry too much about that now because we have a section devoted to this later on. And of course, you could ask the question, well, are there too many specialized mechanisms, and is this really going to be a fair take on what would be a reasonable model of psychological behavior? Again, the motivation for building Clarion is that it is grounded in what we know of psychology and is trying to be a compact, robust, general purpose kind of a system here with identifiable pieces of, say, memory that we know from other research. Yes, it does have semantic and procedural and episodic memory systems within it. It also has a working memory system within it and a way of doing or handling drives and goals. Current work in Clarion is going beyond that and getting into issues of personality and affective processing and so forth. We may not get into that at all today or in the next 2 weeks either, but it is some of the things that are sort of at the leading edge of what we're using Clarion for. There's a bunch of data that you can look at. These are some of the papers that have been prepared of Clarion simulations in the past. Some of these go back quite a ways, 1988 even, and Ron Sun's been working on this for quite a while. And these are some of the papers that have been based on, or simulations that Clarion has attempted to replicate. Has Ronstone started that in '88? I'm not sure. It's later than '93, I think. Here are some more here. These are quite a few of the studies that have been done, and of course, this is always an ongoing problem. No need to get into that too much because we're going to be able to have these slides online later on. But as you see towards the end there, even emulations of moral reasoning and personality can be attempted using Clarion. Finally, here are some of the papers, and they'll be there. And then, of course, the important detailed specification of Clarion, which is Ronson's technical report, which is going to give you far more information than we can do in 4 hours. So if you're interested in the deeper theory or the mathematics that propel a lot of this, you can find that there. And this is how that works. So to conclude this first section here, what is Clarion? Well, it's a comprehensive theory of mind. Cognition is broadly defined. It's a conceptual framework that we can build on. We can analyze various cognitive and psychological phenomena with it here. And we can simulate those data in code in a software system here. And the final thing there is going to be more that we're moving towards a library of components that you can use to build various kinds of agents for a variety of purposes. And that's kind of our ongoing interest in developing Clarion, is that here is a very comprehensive library. Build what you like with it and see how far you can push it. We have no idea what the scalability of Clarion is going forward. We are still building new things all the time with it and sort of broadening the difficulty spaces we're trying to build for it. So before I move on, any questions to end part 1 here?